Okay, let's work 5.79 from the textbook. This question reads, at a certain temperature and pressure, it requires 4.85 minutes for a 1.5 liter sample of helium gas to effuse through a membrane. How long would we expect this to take for a 1.5 liter sample of a different gas, fluorine gas, F2, diatomic, to effuse through the same membrane setup, okay? So when we see this word effusion or effuse, how long does it take, etc., etc., the problem is going to deal with this so-called Graham's Law of Effusion, which is considered on page 236 of your textbook. So you can kind of look that up. But basically what this effusion business is all about is if we put a gas in a container with a very small leak, a very, very tiny hole, the gas molecules, or atoms, will eventually basically pass through that hole to the outside world. That process of the molecules or the atoms passing through the hole is called effusion. It's kind of like a leak from the chamber. And the effusion is based upon the fact that gas molecules or atoms are in constant motion. They're constantly moving. And just by random chance, an atom or a molecule may basically be incident upon that hole and just pass to the outside world and be removed from the chamber, okay? That makes a lot of sense if you think about it. Well, people want to study or have historically studied the rates of effusion of gases through these tiny little holes and basically related that directly to the molecular speed, okay? That's what influences the rate of effusion. Now, because of that, the mass of the particles of the gases becomes pretty important because the mass directly affects the speed, which affects the rate of effusion, okay? So actually you can use effusion rate measurements to figure out molecular weights of gases. And the process is pretty similar to the type of thing that we're doing here because we're still going to use the same law, all right? Now, in your textbook, you will find this law of effusion that is defined in this way. It's comparing two gases, gas A and gas B. And basically what this says is that the rate of effusion of gas A divided by the rate of gas B is equal to the square root of the molecular weight ratios B divided by A. Okay, now these are the molar masses. So the molar masses play a key role in defining the rate of effusion, and that's how you see this law typically show up in textbooks, such as the one that we use for this class. However, if we look at this problem carefully, okay, notice that you're told how much time it takes or how much time is required for the gas to successfully effuse through the hole, and you want to project how long it's going to take for the other gas. Okay, this is a time. Oftentimes, we confuse rates and times, and it's really easy to do. And I wanted to take a second to point this out. What is denoted here is the rate of effusion of substance A and the rate of B. That's the speed at which it effuses through the hole. Now that's related to time, but it's not the same thing. If you think about it, rate and time are kind of inversely proportional to one another, okay? The rate at which something occurs, if it occurs very, very fast, a very high rate, it occurs in a very low amount of time. And likewise, if something is very slow, it has a very slow rate. That requires a huge time, okay? So one thing that your chapter in your book doesn't really do a good job at is making note of that. And if you're not careful, you could get confused between rate and time. Now, to make it easier, what I've tried to do here is to modify this equation that's in your book with kind of an extension here on the right. And I think this will be helpful for you to work this type of problem that they present you with. What I basically did is realize that rate and time is inversely proportional to one another. So instead of writing it in rates, I wrote it out here in the time required for sample A or gas A and the time required for gas B to effuse through the same hole. So here it's just 1 over the time required for substance A, and that's analogous to the rate, because again, they're inversely proportional. And here I have 1 over time required for gas B. And then I've taken this equation and I've simplified it and generated a new equation. It looks pretty similar to this one, but yet it's a little bit different, because now I have the time required for gas B in the numerator and the time required for gas A in the denominator, and then I still have this molecular weight ratio, okay? But nonetheless, once we arrive at this business of this Graham's law of effusion, we can start thinking about plugging in numbers for this particular case to figure out, kind of where we stand, okay? So what I would like to do is first be pretty careful about what I define as which substance, A and B, okay? And the reason why I want to do that is so I don't confuse myself. So I'm going to define helium as substance A, because that's one of my gases in the problem. The other gas is fluorine. I'm going to define that as substance B. I write this on my piece of paper so I can't confuse which one, okay? Because it's hard to remember what's in the numerator, what's in the denominator, what number goes where. It's easier just to write out what's A and what substance is B, so you don't confuse yourself, okay? Now in the equation, I'm told to take the square root of the molecular weight ratio, or the molar mass ratio, for the gases of interest, B divided by A. And since I took some time to write over there on the left which gas is B and which gas is A, it's helpful to me, because now I know that fluorine is the one that goes in the numerator, and I should write about 38 grams per mole here, because it's F2. Each fluorine's about 19, so I just multiplied that by 2 in my head to get 38, okay? So that's the number that goes there. Now in the denominator is the molar mass of gas A, which is helium. Helium is about 4 grams per mole. That's a monatomic noble gas, so F2 in the numerator, but it's He in the denominator. So I end up with 38 divided by 4. I need to take the square root of that, and if I do, I get 3.08. So this 3.08 then tells me the ratio between time required for B divided by time required for A. Now, if I am being a little bit more specific, time required for B, well, that's the time required for F2. Time required for A, well, that's the time required for HE. Remember, those are the inverses of the rates, right? Time required. So that ratio has to be a little over 3. Do I know anything about how long was required for either of these? Well, it looks like in the problem it told me for the helium I required 4.85 minutes. But I don't know how long it takes for the fluorine to effuse. But I know that ratio, x divided by 4.85, has to equal 3.08 by the Graham's law of effusion. So it simply becomes an algebra problem. X divided by 4.85 equals 3.08. Perfect sense. Means X has to be equal to 3.08 times 4.85. Do the math on that, I get 14.94 minutes. Okay, 14.94, just a little under 15 minutes is what it would require for fluorine. All right, so I hope that this has been useful to you. You can see how this Graham's law of effusion thing works. I again want to caution you to remember about this business, this difference between time and rate, because I noticed that a lot of the problems in your textbook at the end of the chapter, and even in the chapter when I'm talking about the Graham's law of effusion, they don't explicitly make this point that rate and time are not the same thing. Okay, if you kind of understand how this works, and you understand that the faster moving gas will effuse more rapidly, and faster moving gases have lower molecular weights, you can kind of put one and one together and figure it out, like how long it would take, just sort of in your head. But if you're not one to do that, and you just start plugging times in here and here, you may end up with getting the wrong answer because time and rate are not the same thing. They're inversely proportional. Okay, so if you want to use the modified equation, feel free to do so. But I think it is important to bring this up as a potential problem area for you when you get on the homework problems or you get on the exam.